Hello class, this is lesson 4.1. Here we will learn about polynomials. So this is the general form of a polynomial, and it may look scary as a general form, but when we plug numbers into it, they are not that complicated. So it's just a number times x to the n plus another number times x to the n minus 1, and so on. And we request the first term be non-zero, but it's okay for some of the middle terms to be non-zero. And the term with the biggest exponent, here is called the leading term. So an x to the n is the leading term. Okay, so to demonstrate what is a polynomial and what is not a polynomial, I drew a few functions here. Let's look at them. The first one is 3x to the 9 plus 2x to the 7 plus x. So this is a polynomial because it's just a number that's a exponent. The exponent is a positive integer, I forgot to mention. And a number, the exponent's a positive integer number. There's no exponent, but it's really like an exponent of 1. So everything's satisfied. This is a polynomial. If we look at the next example, though, we have real numbers as the coefficients, or the numbers multiplied to x. So that part's satisfied, but the exponents here are not integers. They're not positive integers. So this is not a polynomial. We just want nice whole numbers as the exponents. Okay, let's look at the next example. It's fine to have a decimal as the number being multiplied to x, as long as it's just a real number. So this is fine, this is good, it's fine, that's fine. And it's okay for the last term to just be a number without an x. So this is a polynomial. Okay, the next one. Well, it looks okay on top. It's a number and then an integer exponent. So everything's fine, but the problem here is we have x's on the bottom as well. Right, so that we cannot have a rational function that is not a polynomial. We don't want any situations like this. Okay, so hopefully that gives you an intuition of what a polynomial is, and we have been working with polynomials every now and then. In the previous chapters, we just did not explicitly call them polynomials. Okay, now we're going to investigate the leading term a little more now, because the leading term is the most important term. And if we think about it, there is 4 cases for the leading term here. So I'll break it up into 2 categories. Either the exponent is even or the exponent n is odd. Now when you have an even exponent in the leading term, then the number in front of the x could either be positive or negative. So I drew some examples here in green. So notice here our leading term is 4x to the 16. Even exponent, positive number. Here the leading term is negative 3x to the 8. Even exponent, negative number. Okay. Now in the other category, we have odd exponents in the leading term. It could be either a case like this, we have an odd exponent and a positive number, or an odd exponent and a negative number. The reason why I categorize these cases in this way is given by the following template here. We know the sort of basic shape of the graph just by knowing the leading term. So in case A1, when n was even exponent, positive number, the basic shape of the graph will look like this. Now why did I do a squiggly line here in the middle? Because just using the leading term, it doesn't tell us the behavior here in the middle. It only tells us the end behavior, or the behavior when x is either really positive, when x is really negative. And that should make sense. Let's look at this example. If we plug in really big positive numbers or really big negative numbers, then the leading term will dominate all of the smaller terms. So for really big or really negative x values, the leading term is all that matters, and this stuff is just a little bit irrelevant after a while. Okay, so then if we have an even exponent and a negative number, the end behavior will look like this. Okay, now another way we could write this is, here notice when x is going to positive infinity, let's say the function, let's call this the function f is going to infinity, positive infinity. But when x is going here to negative infinity, f is going to positive infinity. Right, when x goes to minus infinity, f goes up to positive infinity. Here in case A2, we have x goes to positive infinity, f goes to negative infinity. X goes to negative infinity, f goes to negative infinity. Okay, so that is the two end behavior cases when the exponent is even in the leading term. Now when the exponent is odd, we have these two end behaviors. Either when the number is positive, we get the x goes to infinity, f goes to infinity, x goes to minus infinity, f goes to minus infinity. Or over here, if the number is negative, then we get x goes to infinity, f goes to minus infinity, x goes to minus infinity, f goes to positive infinity. Here is the 4 cases and a rough sketch of the graph of all these cases. Okay, so it may help to take a screenshot of this and just sort of memorize it. But anyways, I will move on and do some examples now. Okay, so we're given a function here and we want to describe the end behavior. Well, first we need to identify the leading term. Now we got to be careful. The leading term is the term with the biggest exponent. It's not always written first. So here this is the leading term because 9 is the biggest exponent here. So what case are we? Well, we have a negative number, odd, right, and an odd exponent. And therefore we are in this case, negative number, odd exponent. So plugging into the template here, we know the graph will look roughly like this, right? Where we know as x goes off to infinity, the graph f is going to go down to minus infinity. As x goes to negative infinity, the graph will go to positive infinity. Right, so x gets big, f goes down to minus infinity. X gets negative, f goes up to positive infinity. Okay, let's now look at the other example here. So first we need to identify the leading term. Okay, we have an even exponent, positive number out front, and therefore looking at the template, we know it will behave roughly like this. Or that as x goes to infinity, the graph will go to infinity. As x goes to minus infinity, the graph will also go to infinity. Okay. Okay, so moving on, let's talk about the zeros of a polynomial. And what I mean by that, well, we've already seen zeros of a function. And chapter 1, I think, is the same thing here. A polynomial is a function. But anyways, I wrote it down. So let f of x be a polynomial. The zeros of f are the x values such that f of x equals 0. Okay, so finding these zeros sometimes are easy, sometimes really difficult. We've already seen quadratic functions before. A quadratic function is when something with a leading term of 2, the exponent is 2. So we've seen quadratic functions like this, and those are easy to factor, and we can solve those. But here we sometimes have higher order problems that are not always quadratic, and we have to be a little more clever when factoring them. So I have these two examples here where we have to factor them using a few different methods we may or may not have seen before. How I'm going to factor this is called factoring by grouping. What that means is I sort of group these two terms together and I group those two terms together. Right? So I'm going to think of these two terms as one group and these two terms as another group. Okay? I'm going to think of those and I'm going to think of these. Okay, so if we look at this first group, we have x to the 3 and x to the 2. So I could pull an x squared out of both of those. Right? I could pull x squared out of both of those terms and would be left with x minus 2. Or if it helps you, if I multiply this x back in, I would arrive where we started. Okay. So now let's think of this other group. I'll do the other group in green. They both have a common factor, right? They both have a 9 in there, so I could pull out the 9. I'll pull out a negative 9, say. Yeah. Pull out the negative 9, I'm left with x minus 2. And if it helps, you could multiply the negative 9 back and you'd end up where we started. Okay, so why did I do that? Well, now let's think about the whole thing. Now we have a common factor here. The x minus 2 is a common factor in both of these groups. So I could actually just pull the x minus 2 out of these big parentheses here. If I pull the x minus 2 out, I'm just left with x squared minus 9. Okay? So that was convenient. And now x squared minus 9 factors quite easily. So if we factor the x squared minus 9, we have x minus 3x plus 3. Okay? And if we want to find the zeros of this, well, we set everything to 0 and solve for x. So the zeros would be 2, 3, or negative 3. Right? That is to say, if I plug in a 2, if I plug in a 3, or if I plug in a negative 3, this whole thing will equal 0. And that's what we were, if we want to find the zeros, we set everything to 0. Okay, so this is called factoring by grouping. Okay, now let's factor this one to find the zeros, so set it to 0. We've seen problems like this before. We need to let u equal x squared, and then we get the u squared plus 4u minus 45. Right? And then we can factor this. So that's u, let's see, is it plus 9 and minus 5? Okay, so u will equal negative 9, or u will equal 5, but u is x squared, so x squared equals negative 9, or x squared equals 5. Right, so take the square root of both sides, x will be plus or minus square root of negative 9, which is 3i. Take the square root of both sides of here, we get plus or minus square root 5. So notice there's two answers, there's 4 answers in total. It's no coincidence we get 4 answers and the leading term had a 4 as the exponent. that usually will happen unless the equation factors in a really perfect way, like x minus a to the fourth will only have one answer. And that leads us to the next topic. It's called multiplicity. How a multiplicity is just this, a value, the number of times a factor is, let me rephrase that. The multiplicity of a factor is simply these values here. So the multiplicity of this term x minus a is n. The multiplicity of this term x minus b is m. And just the number of times this factor appears. Okay, so let's say a polynomial is factored in this way, x minus a to the n, x minus b to the n. Well then, if we set the whole thing to 0, then clearly the zeros would be a or b, right? So I'll put a and b just on the number line here on the xy plane. And let me ask you the following question. Is the graph going to cross the x-axis at a and b, sort of like this? Is it going to cross? Are we going to cross the x-axis? Or is the graph going to just bounce off the x-axis like this? Now there's actually a way to tell just by studying the multiplicity. Really, and all that matters is whether or not the multiplicity is even or odd. So let's just consider one of these terms here, x minus a to the n. So n is the multiplicity. If the multiplicity n is even, then the graph bounces off the x-axis. So if we have an even multiplicity, the graph will bounce off the axis there. If the multiplicity is odd, then the graph does cross through the x-axis. So if we have an odd multiplicity, the graph will go through. Okay, so that's a really convenient fact, because now we could even do a rough sketch of a really complicated graph like this. Because here we have, it's factored for us, but just by studying these multiplicities, we could do a rough sketch of the graph. We have to do it in the following way. First, let's think about what would the leading term be. What is the leading term here? Well, you'd have to multiply it all out to get the leading term, but it's quite obvious that from this term here, if we square it, we'd get an x squared. Here we'd get an x cubed. Here we'd just get an x. So x squared, and then times x cubed, and then times x, right? We would get something like an x squared times an x cubed times an x, or an x to the 1 if you prefer. So the leading term would be x to the 6. So we have an even exponent. It's kind of like there's a number 1 there, which is positive. Okay, which tells us the end behavior looks sort of like this. But now that we have knowledge about the multiplicities, we can get a more accurate sketch of the graph. We could get the middle behavior. Right, so let's investigate what the graph will roughly look like. Well, it's going to cross or bounce off the x-axis at either 3, 1, or negative 1. Why? Because if you plug in a 3, a 1, or a negative 1, then the whole thing will equal 0. Okay, and we know the end behavior will look like this because the leading term had an even exponent and a positive number multiplied to it. So now the question is, does the graph bounce off of these points, or does it go through the points? And we know that by looking at the multiplicity. So what's the multiplicity of the negative 1 term? That's here. If we plug in negative 1 to this term, it gives us the 0. The multiplicity is 1, which is odd. So we cross through this guy. What's the multiplicity of the 1, 0? Well, if we plug in 1 here, we get a 0. And the multiplicity is 3, which is odd. So we cross through there. What's the multiplicity of this? We get a 0 if you plug in the 3. the multiplicity is even, so therefore you bounce off of this. And that's a rough sketch of the graph. So this knowledge is pretty convenient. We can sketch some really complicated polynomials just by factoring. Okay, and that concludes today's lesson on polynomials.